Welcome. This talk is about the profiling support provided by NOELLE that builds upon LLVM. This talk is for my class Advanced Topics in Compilers that I teach at Northwestern University. I've decided to open these talks to everyone, even if they are not professionally made, with the hope they will be useful for anyone interested in doing compiler research while taking advantage of the NOELLE framework. This talk is organized in 3 parts. First, we're going to look at how to profile using NOELLE, then how to use the information generated by the profile phase, and finally, what is special about loops that we provide and their profiles. All profiles provided by NOELLE is about the number of dynamic instructions that are executed within a code region. And in particular, it is about the cumulative number of dynamic instructions executed in a code region among the whole program execution. So therefore, for example, let's say that we know that we have executed a certain number of dynamic instructions in a function foo. That is the sum of the instructions executed in foo when invoked by another function bar and when invoked by another function main. So the profiles that NOELLE provide does not distinguish between the subset of dynamic instructions executed in foo when coming from bar and the subset when coming from main. Is the sum of them. In order to profile, you first need to normalize the IR, as every time you need to use NOELLE. Then you have 3 phases: generate, run, embed. In the first phase, generate, you have to generate the binary that includes the instrumentation code that will collect information at runtime. Here, you have to use the tool NOELLE prof coverage. You have to pass an IR that is being normalized by NOELLE, and then the name of the binary that the NOELLE prof coverage tool will generate, which will include the instrumentation. And every compilation options you need to generate a standalone binary from the IR given as input. In this particular case, we need to link with the math library and the standard C++ library to generate a standalone binary. In step 1, you need to run the binary and you need to provide the input or inputs that are representative to what you expect to find in production. So in this case, I'm going to run my standalone binary, passing my input called my input, or in this case, my binary takes 3 inputs that are 3 integers, and I pass 10, 20, 30 because I think this is representative. Or in this case, I pass a name of a file. Whatever is the input that your program needs, you have to provide it. Finally, the profile information is now generated by step 1, and a new file is created in the process in step 1 called default.profrow. Now we want to take this file and embed it inside the IR. So then you only need the IR to keep the IR with you, and all the information is embedded in it. In order to do that, NOELLE provides a tool called NOELLE meta prof embed, which the first argument is the profile information generated by step 1, and you can have many of them. You can merge them using an LLVM tool, but in this case we only have one. Then the name of the IR file, and then this IR file has to be exactly the same as the one you've used in step 0. And finally, the name of the IR you want to generate, which will differ from the IR.bc only by having the profile information embedded in it. Now you can access the profile information from your path that you build upon NOELLE, like in this case. So now the question is, how can you access the profile information? In order to fetch the profiles, you first have to fetch NOELLE, and then you have to ask NOELLE to give you the profiles by invoking the method getProfiles. Now you have an object. Here we call hot because it's an instance of the class hot, and you can use the public API of this object to query the profile. The first important one is the method is available. If this one returns false, it means NOELLE couldn't find any profile information embedded into the IR. If instead it's true, you have the full profile information. The public API, you can find it in this header file. The queries that you can ask the hot object are about a code region X, where X is an instruction, a loop, a function, a basic block, or a strongly connected component of a dependence graph. like for example of a loop dependence graph. And you can ask, has X been executed ever? Or how many times X has been executed, for example. If X is a loop, how many times the loop itself has been executed? Or how many static instructions compose X? Or how often a branch is taken? Now, these branches are related to X. You can ask for any branch in the program. Now, there is a concept that we have in the public API called self, total, and static. And this one resembled what you have in typical profiling tool like gprof. So static is the number of static instructions that compose X. Self is the number of dynamic instructions executed within X for the whole program execution without counting instructions executed by callees. And total instead includes the dynamic instructions executed by the callees. So there is a set of APIs that you can use for every single code region, X. So for a loop, for a function, for basic block. And the signature is the same with the only exception that the object given as input that identify the code region is different. For example, if you have a function and you want to see if the function has been executed, then you can invoke the method has been executed. And if you pass a function, it gives you information about the function. If you pass a loop structure, an instance of the class loop structure, you get information about whether that loop has been executed. If you pass a basic block, it gives you information about that basic block. Also, similarly, you can ask the hot profiler to know how many dynamic self-instructions has been executed in a given region. So in a function, in a loop, in a basic block. You can also ask for the total number of total dynamic instructions that has been executed in a code region. And you can also ask the profiler how many static instructions compose the code region. This is of course not computed with the profiler. This is static knowledge, but it's just convenient to have that API in the same class. Finally, you can query about the coverage using the total instruction count for a given region, where the coverage is for the whole program execution. So you can ask how many, so for example, if you ask get total instructions of a function, in this one returns 30, it means for the whole program execution, 30 instructions has been executed within F. But if you ask get dynamic total instruction coverage of the same function, it gives you a number that is between 0 and 1. So between 0 and 1 represents 100%. And if that number comes back to be 0.5, it means that the 30 dynamic instructions that were executed within F represents half of the total number of dynamic instructions executed in a program. There are some APIs that can only be used by a subset of the code regions of the X. In particular, this API can only be used for every code region but a strongly connected component. And this API is get invocations. The reason is because the number of invocations of a function, of a loop, of a basic block, of an instruction is well defined. But for a strongly connected component of a dependence graph is not well defined. What does it mean, an invocation of an SCC? An SCC can be part of a subloop or not. So then the concept of invocation is blurry. So that's why we don't provide the support for that, as the concept is not well defined. Some X has extra queries you can ask that are not available for other X. So you can query extra information. You can do extra queries for loops, for example, that don't make sense for another code region, like a function. So for example, if you have a loop, an instance of the class loop structure, you can ask the profiler object, give me the average number of loop iterations that have been executed per invocation of this loop. Obviously, this is a query that can only make sense for a loop, not for a basic block or a function. Now let's look about loops and their profiles. So NOELLE provides API to sort loops by their profile, in particular by their coverage. So you can take a vector of loops, for example, the one returned by getLoopStructures API of NOELLE, and you can sort them by coverage. And then after you do that, they are sorted in place, so the container is modified, that the one you pass as input. And then the result is that if you now take the first element of this container, you get the loop with that, which has the highest number of total number of dynamic instructions executed compared to all the loops. With this, thank you for watching, and I hope this helps.